Hello and welcome to this talk on an effective field theory approach to resonant production of massive particles. This is a part of the online effective field theory course. My name is Deepjyoti and I'm a research scholar at the Tata Institute of Fundamental Research. The problem with massive particles is that the propagator has a singularity at resonance. Now, this can be cured by a finite width of the particle by inserting that finite width, and there are many approaches along these lines, and one of the approaches and one of the most successful approaches is the approach by effective field theory. Effective field theory aims to calculate the propagator and increasing accuracy order by order in perturbation theory. Now there are two expansion parameters in this problem. One is the coupling constant alpha, and another is the ratio r, which is the ratio of the width by the mass. It is assumed that the decay width of this particle is very small and the mass is very large, and that is why we can use this approach as we can use this ratio as a very good expansion parameter. What I'm going to say in this talk is derived mostly from these two papers, both by Beneke et al. The first one is basically an expansion of this paper, the second paper, okay, and unless otherwise mentioned, all of the stuff that I'm talking about has been taken from these two papers. So the scales involved in this problem are important to note down, and we'll note it down once and for all. There are primarily two scales involved. One is the pole mass, and another is the decay width. Now it is important that the decay width is much smaller than the pole mass. Okay, we can then make particles near resonance. How near resonance? By near resonance we mean that s minus m square is of the order of m into gamma. Now, m into gamma is much smaller than m squared, and thereby we can define another small parameter which is s minus m square by m square, which is of the order of gamma by m, and this we'll call delta. So we'll have two small parameters. One is the coupling constant alpha, and another is the small expansion parameter delta. Now when a heavy particle is formed, the production and the decay timescales are of the order of 1 by m, which is very small because m is very large. However, the propagation is of the order of 1 by gamma. So the decay and the production vertices are basically they factorized from one another, and you can also describe the production as the propagation independently of these two vertices. Now we'll deal with a very simplified model, and the simplified model that we have is basically the production of a heavy scalar by the scattering of two Dirac fermions. We'll have an electron, we'll have a neutrino, and the process will be colliding a neutrino and an electron and producing a very heavy scalar x. That x will then decay and again give us an electron and a neutrino, and the electrons and a neutrino are collinear, and this x is produced very near resonance. It is up to the experimenter to make sure that the energies of this of the pair of electron neutrino comes very close to the mass of x. That is left up to the experimenter, and our theory will be dealing with only that region where s minus m square is of the order of m into gamma. Okay, so here is a representation as the Fineman diagram of the process where the thick line in the middle is the heavy scalar x, and that is given by the heavy scalar effective theory. Okay, so we'll have a Lagrangian for the heavy scalar effective theory. These lines, which represent the electrons, the incoming electron over here and the incoming anti-neutrino, these are collinear, and thereby they are given with the soft collinear effective theory Lagrangian. And this interaction vertex is a Yukawa type vertex. We will have the Yukawa type vertex. We'll also have another interaction type vertex, which is the 4 Fermi interaction, which is basically obtained after the scalar has been integrated out. So we'll approach each of this systematically. So we'll be calculating, our aim will be to calculate the line shape at leading order first, and then we'll go on to beyond leading order and calculate the same line shape at next to leading order. Now at the leading order we have the effective this heavy scalar effective Lagrangian, and this is very similar to the heavy quark effective theory, except that it's not for a quark, it's for a scalar. So we take the we similarly take P equals to mv plus k, where k is the so-called tickle, mv is the, the major part of P, k is very small, v square is 1. All of this is very well known. The scalar field, we take away e to the power of I mv dot x from the scalar field and define another field which is phi v, which is an annihilating field, and that appears in our Lagrangian. There are of course other fields such as the soft electron neutrino, so this is not the whole story, but just for the scalar effective field theory we have this kind of a Lagrangian, which is very similar to the HQET Lagrangian. Now to note a few things, here is 2m, and the m with a hat is the renormalized mass. Okay, this normalization is mostly a non-relativistic normalization, so we'll have a 2m. We have to keep track of this 2m later on when we do a matching. This covariant derivative is a soft covariant derivative, which is it's the fact that it's soft is denoted by the subscript s, and the soft covariant derivative basically means that the A field inside is a soft photon field. So we have that. We have the soft photon field kinetic term over here. We have the soft electron field over here, and finally we have the soft neutrino field. Now the electron field obviously does interact with the AS, and therefore we have a ds slash. The neutrino, however, is neutral, does not interact with the AS, and simply the ordinary derivative suffices. So this is our scalar, heavy scalar effective Lagrangian. And a couple of comments. I repeat the Lagrangian, and it's worthwhile to point out that this factor delta over here is a matching coefficient. We'll have a lot of things to do with the delta later on. So this is dependent on the normalization scheme. We will see how it depends on the normalization scheme later on, and this is found by matching to the full theory. So we'll calculate say a Green's function with respect to effective field theory. We'll also have a Green's function from the full theory, and then we'll match, and then we'll see what this delta comes out to be. It's also worthwhile to note the scaling of the various quantities. The scaling of the various quantities is just given by this kinetic term. The ds obviously is just delta. Okay, the covariant derivative, the photon fields, just scales as delta, and if this scales as delta, this whole thing must scale as delta to the power of 3/2, because this thing scales as delta to the power 3/2, because the whole thing must scale as delta to the power 4. Okay, and that settles the scaling of phi v. Okay. This, however, is just the scalar part. Okay, it is also necessary to note the collinear modes of the electrons and the neutrinos. So this is the soft part, and also this is just the scalar part. So the collinear Lagrangian for the electrons and the neutrinos is actually dependent on the vectors that are chosen. So you can have two very energetic particles, the electrons and the neutrinos, and you have two light-like vectors for the electrons and the neutrino, which is given by n plus and n minus. And say we have n plus as 1 0 0 minus 1, and n minus is 1 0 0 1. Both are of obviously light-like vectors. Then obviously the square, the n minus square or n plus square is 0, whereas n plus n minus is 2. This is just this is a property of light-like vectors. So the momentum can actually be split, and this is extremely easy to obtain. They can be split into direction of n minus, the direction of n plus, and transverse. Okay, so these are just two opposite directions, say z plus and z plus z and minus z along the z-axis or against it, and this part represents the part of the momentum which is going in the transverse direction. And the collinear condition is just this part, this part which is the coefficient of n minus, the direction in which the electron is going. That has to be a hard part, which is just m, because the electron is obviously very hard. It's collinear and you have n plus p is of the order of m. N minus p is of the order of m delta, because that has to be very soft, and the transverse is just m delta to the power half. That is the collinear condition that we'll adopt. So we can then write down the soft collinear effective Lagrangian, and this is something which we are all familiar with. And here the derivatives are the covariant derivatives with respect to the collinear fields, and the collinear fields are here you have the collinear electron field, here you have the collinear covariant derivative, where the A which appears is the collinear photonic field. You have the collinear photonic field kinetic term, and that is the soft collinear effective Lagrangian. We also have the interaction Lagrangian. We need an electron neutrino scalar vertex. Remember, none of these two Lagrangians has an electron neutrino scalar vertex, so we need an electron neutrino scalar vertex, and that is given by this kind of a Yukawa type interaction, which is the electron over here, the neutrino over here, and a scalar vertex, the Hermitian conjugate of that. And of course you can also have a 4 Fermi interaction with this. Okay, you can have a 4 Fermi interaction. So we started off trying to calculate the leading order line shape, and the first step in the calculation is to get this coefficient delta. And now that coefficient delta can be found by matching to the full theory. And if you match with the full theory, you have this self-energy correction term, which is pi. It's given by pi at the pole mass, and when you calculate that, you have these kind of diagrams where you have the photon loop with the fermion loop, the photon and the fermion forming a loop over here, and this is the counter term. And these are results that are quoted from the paper, and this is the after a lot of calculations, this is what you get. Okay, and you can understand that this here you don't have a 1 by epsilon, and the poles, the singularities have vanished, and the scheme of renormalization has to be, the scheme of renormalization used here is ms bar. The scheme of renormalization is very important over here, because the ultimate answer for pi depends on that renormalization scheme, and since pi depends on the renormalization scheme, delta will also depend on the same scheme of renormalization. So delta changes if you change the renormalization scheme. Now here, if you define the pole mass to be the singularity of the propagator, then you have this kind of a relation, and you put that to 0. If you put it to 0 and expand the pole mass as some ms bar mass plus a delta m, then you can just find out that this is just matching these two, putting p equals to mv plus k. You can just find out that this is the result. Now we can then match the real parts and the imaginary parts, and the real parts and the imaginary parts can then match on to the real parts and the imaginary parts of pi, which is itself related to delta. So delta is equal to pi by m, and delta m then becomes related to delta to leading order. The gamma becomes related to the imaginary part of delta to the leading order. Okay, and once we put in the value of pi, and pi is of course related to delta over here, this is the only part which comes out imaginary, and thereby gamma is simply alpha y by 2. Alpha y, remember, is y star by 4 pi. So alpha y by 2 into m being the renormalized mass over here, m hat actually. Okay, this will come in handy in a couple of slides. So the Feynman diagram that we should calculate is simply this. Okay, and the Feynman diagram is extremely simple. We just put in the propagator over here, the scalar propagator over here, and we have the Dirac spinners on either side. Take the polarization average, put in v equals to 1 0 0 0, and because the scalar can be almost assumed to be sitting there and not doing anything. P is of course in the direction of n minus, q is in the direction of n plus p, being the vector for the electron, q being the vector for the neutrino, and p plus q will obviously be equal to mv plus k. I take the spin average, put v dot k, put all these factors, v dot k comes out to be root s minus m, and this amplitude is simply given by this simple formula. An important thing to mention, important thing to note here is the presence of this m, which is just the square of the center of mass energy in the numerator. And then we used the optical theorem. And the optical theorem basically says that the cross section is related to the imaginary part of the amplitude. This is all to leading order, that's why we have zeros over here. The 1 by s over here cancels the s in the numerator in a naught, and we simply have to take the imaginary part of this propagator. And once we do that, we find that the imaginary part which was related to gamma, the width over here, like this, we had derived this result a couple of slides back, and that comes in the numerator, and this is the final form of the cross section. Now this form of the cross section is exactly the Bright-Wigner form that we are familiar with. We are familiar with the Bright-Wigner form, very near a Lorentzian for a particle which is produced at resonance. And this is what the Bright-Wigner would look like. This plot has been plotted for the z, where z, the peak is just somewhere above 91.6. Okay, this plot is taken from the paper that I was referring to earlier, and we have they calculate the decay width both in the combined theory and in the effective theory, and the effective theory is given by this solid line, okay, and the combined and the full theory is given by this dotted line, okay. And if you combine, then the effective theory does extremely well where there is a resonance, okay, much better than the full theory, but the full theory does very well away from the resonance. So the combination of effective theory and the full theory is very important, because we would want a very faithful representation of what happens, of the faithful representation of the line shape of these kind of unstable particles. Right, now we should sail forward and calculate the line shape at the leading order, and this will require a lot of technical matching that we have to be very careful about. So let's just see, if we take the next to leading order, then we need to write down the Lagrangian to next to leading order. Okay, we again have to do the things that we have been doing. We have to calculate the renormalized Green's functions, the propagator, in the full theory after the desired order in alpha or delta, and we have to do the same thing in the effective theory and then match. Okay, and we have to match the coefficient of the desired accuracy. The problem is this often gets very messy. So we will need to do three things. We will need to make sure that our heavy scalar effective Lagrangian, which we had written down earlier to just LO, that's the leading order, we have to expand that to NLO, and then match delta. We just matched delta to leading order earlier, now we have to match delta to next leading order. Similarly, we have to do a similar job for the scalar, the soft collinear effective theory. However, we will see that won't be needed. We also have to correct for the vertices, because the vertices taken earlier were to leading order. Here, leading order vertices won't work. We have to consistently expand. We could consistently take the one loop correction to the leading order vertices as well. So this is the rough blueprint. We'll to see how we go along. First, the heavy scalar effective theory. The heavy scalar effective theory, the propagator is of course again at resonance, and R phi is the LZ residue that you find, and you put this part, this p square minus s, p square is of course mv plus k, put it back over here and put that to 0. Okay, if you put that to 0, then you can have a solution to vk. Okay, because remember the Green's function has to vanish. Over here we get a relation for vk with delta. Okay, and we have also introduced this variable k transverse, k transverse is nothing but the part of k which is not in the direction of v mu. So if we get this kind of, we do binomial expansion from this step to this step, and we get this kind of relation between vk and delta and k transpose, transverse. And just a reminder, so the LSHSET will then look like this, where this was the term which we were familiar with, and this is the new term. New term is in red. This is the new term. This new term is just given by the Green's function that we had calculated earlier. Just that we have just put in delta square by 8m minus the k transverse just becomes ds transverse all squared. Okay, so this is the term that we have new. However, we are not out of the woods yet, because these are of order alpha square or alpha delta or delta squared. That means they are of second order. These are of first order. However, delta itself can be of second order if you calculate delta to NLO. So delta can have a part which is leading order and a part which is next to leading order. Now you can calculate delta to leading order, next to leading order, and just be quoting results. You have to match it to the full theory. You have to do the whole calculation, the full theory and the effective theory, and then match. Then we get these expressions. Again, this expression is something I quoted earlier. This expression is taken from the paper, and you can see that this one is an order higher than delta 1. So the LHSET over here is not exactly the thing that we're looking for. We're actually looking for this kind of a Lagrangian, where you have the first order delta sitting over here and a second order delta over here. You've borrowed this first order delta, taken the second order delta over here, and this is a second order term. So these terms are all NLO terms. These terms are all the LO terms that we were familiar with. The delta we were speaking of earlier is this delta over here. The delta 2 is the new delta calculated to second order. Nice. So you include all the soft photon terms, and there are no extra terms over here. You just include all the soft photon terms with having the kinetic terms and the interaction terms over here, and they form this kind of, this is the full heavy scalar effective theory Lagrangian at NLO. Now it turns out that the soft collinear effective theory Lagrangian is fine. It's just fine at leading order. You can have all types of vertices at leading order, and that is because this can be written in terms of Wilson loop. So there are no relevant operators at this order that we have to introduce, and therefore the leading order Lagrangian is fine, and thereby we would be happy with this. Okay. Now we had another thing that we had to do, which was correct the vertices, and the vertices were calculated to LO earlier. Now we have to calculate to NLO. And at the tree level, this was the decay, this was the 4 Fermi decay vertex. Okay, we have to calculate the one loop coefficient of this, and the one loop coefficient will come from this kind of an operator, where you have a W over here, which is just the Wilson loop. The Wilson loop is of course got by integrating out the hard 5e fields. It's defined over here, and you just have a WC1 because you can have a collinear photon from an electron, but the collinear photon from neutrinos are of course not possible because the neutrino is neutral. So if you have this kind of an operator, you have to calculate the coefficient of this operator, and the coefficient of this operator can be calculated by matching. So suppose we have amputated ms bar renormalized 3-point function for the E, the nu, and the phi in the full theory, and you can just match the residues multiplied by the vertex over here would match on to the residues of the effective operators and the vertex in the effective theory over here. You have a if you had a non-relativistic normalization to the scalar field, and that crops up over here, and the C is the coefficient that we are looking for. However, this becomes simpler in the ms bar scheme, in the dimensional regularization scheme followed by ms bar. And the dimensional regularization, the one loop in the effective field theory just vanished, so all all the residues in the effective field theory just becomes 1, and since the 1 loops vanish, the gamma given is just the tree gamma that we have. So this is simple, and then I quote results from the paper, and these can be calculated, and there are poles over here, and there are double poles given by the 1 by epsilon square term over here. You put all of this together, and C at NLO is found to be this. Now this still has the double pole and the pole over here given by the 1 by epsilon term, and this will be important in a couple of slides because they'll cancel amongst each other, cancel with the softer terms made from other places. So just to summarize, over here we have the propagator correction. The propagator correction introduced delta 1 squared by 4 and an m delta 2 term. So you have a delta 2 second order term coming in, and the delta 1 squared by 4 coming in with the correction of the propagator, correction of the LO term that we had. The vertex correction gave us a coefficient C1, and there are 2 vertices. One is the production vertex and is the decay vertex, and we have to multiply that by 2. The 4 Fermi vertex gave us an S by 2m hat, and these are the corrections which will come, which we have to multiply the amplitude at the leading order to get the next leading order amplitude. Of course, there are also soft photon diagrams, and you can have soft photon emissions, and the soft photon emissions will also contribute. Of course, this soft photon emission just goes to 0 because the coupling of the photon with the collinear electron is proportional to n minus, and since you have 2 of these, the n minus square comes in as the in the amplitude of the diagram, and n minus square is just 0. So that helps us, of course. So we just have to consider these 2 diagrams, and if you do consider these 2 diagrams, they contribute this kind of a value. So earlier we had a propagator correction which was just this, and the 4 Fermi correction just this, where this curly d is just given by root s minus m minus delta, and if you put all of this together, then we have the amplitude to the first order. The amplitude to first order is what we were looking for. This will give us the line shape to the NLO, and once we have this, we can again use the optical theorem, and I'm not going to do this explicitly because it's very messy, but you can take the imaginary part of the 2 amplitudes summed up together, divide by s, and that will give us the cross section which we can then plot. Now these 2 plots are again taken from the paper, and the upper plot over here, the solid line, it represents the cross section as is obtained from the MS bar scheme, and the broken line is the cross section obtained by the pole scheme. The upper line is the NLO cross section, and the lower blue line is the LO cross section. And remember, around the resonance point, this differs from the Breit-Wigner form, and that is even more apparent over here. The broken line over here, broken magenta line, is the ratio of the Breit-Wigner to the NLO cross section, and the NLO to the Breit-Wigner cross section, and this deviates from 1 quite a bit. So it's not the Breit-Wigner form. It's even at just at NLO. At LO we found the Breit-Wigner form, but at NLO we find that the line shape for a heavy unstable particle is really not the Breit-Wigner. It changes. So that is all that I had to say. As conclusion, we have the propagator of an unstable particle. The effective field theory allows us to have an order by order expansion in perturbation theory, and that is what we did over here. We calculated the leading order line shape and the next to leading order line shape. We calculated this from the effective Lagrangian, which had 3 parts: the heavy scalar part, the soft collinear part, and the 4 Fermi interaction. The LO line shape came out to be Breit-Wigner, but the NLO is not really. It deviates from the naive Breit-Wigner form that we might have assumed. So that's all that I have. Thank you.